Hi everyone, I'm Brendan Devenny. I am a lead engineer, also at Form3 Financial Cloud. So, firstly, a little bit about Form3 itself. So, Form3 is a fintech scale-up on a mission to make payments faster, easier, and more cost-effective for the global financial community. And we're doing this by delivering real-time payment technology. Payment infrastructure is notoriously complex, it is expensive to maintain, and it is prone to risk. Form3's payment technology platform enables financial institutions to entirely outsource this function, so they can focus more on the things that they are good at: innovation, servicing their customers better, etc. The burden of these complexities, therefore, falls on engineers like Piotr and myself. Before we get into the context, a little aside. Form3 are very heavily invested in supporting the industry around us, particularly young women, non-binary people, and ethnic minorities, with a burning passion for technology. If you don't already, please do consider finding a way to have a similar impact on the generations to come. Now, before we get into the technology side of things, I will give you some context around what we are actually building. So, as a single integration payment platform, it's our responsibility to integrate with a rapidly growing list of payment schemes across the world. This is everything from international SWIFT payments to the single European payment area to a place closer to home, at least for me, in the UK faster payment scheme. So this talk will focus on our recent adventure to become a faster payments gateway in the faster payments scheme. This is a concept which I will elaborate on shortly. And of course, how HAProxy helped us deal with a complex matrix of networking requirements, security controls, service level agreements, and maintenance schedules. So the important word to remember in all of this is faster. Faster payments must be handled within a matter of seconds, otherwise they will be reversed, i.e. returned to sender, which leaves us very, very little room for downtime or even for latency. So, what is the faster payment scheme? The faster payment scheme interconnects banks in the UK, with its original objective being to reduce the settlement time for bank-to-bank transfers. So there is a scheme in the UK called BACS, which promises to settle payments within 3 working days. And there is a scheme called CHAPS, which promises to settle payments by the end of the current working day. With faster payments, the aim is to settle payments in seconds. As such, the scheme expects gateways and participants to be always on. Any maintenance must be planned well ahead and communicated well in advance. And any downtime caused by this has real-world impact on the end users who are simply trying to move money around, pay their friends, pay their family. So, some stats which speak for themselves. In 2020, over 2.9 billion payments with a combined value of over £2.1 trillion were processed by the faster payment scheme. This year, so far, Form3 have already processed hundreds of millions of payments. So I will leave you to do the maths and work out a rough percentage there. Otherwise, I will do the maths and I won't sleep tonight. The faster payment scheme has 3 main actors, which we'll be concerned with in this talk. Firstly, we have participants. These are the banks who act on behalf of their customers. Participants connect to a gateway in order to send and receive payments. You then, of course, have gateways. These are the systems which connect participants to the central infrastructure. In some cases, participants are also gateways, such as Monzo, who famously took their FPS gateway in-house to take full control of their own destiny. And finally, you have the central infrastructure. Sometimes this is simply referred to as the scheme. And this is the core of the faster payment system through which all payments flow. It is the single source of truth, it is the ledger, and it is the deity that we all pray to before bed at night. You will also see on this diagram reference to the Bank of England. It plays a very important role, but we are simply going to ignore it today for the sake of simplicity. And that will be the only time in my career I can ever ignore the Bank of England. So, for the context of this talk, keep in mind that Form3 are a gateway. That means we have to worry about interfacing with both the participants and the central infrastructure. And I will now hand over to Piotr for a deeper look at our architecture.
Thanks, Brendan. And now we get to the architectures and the decisions and requirements behind it. So from Form3 point of view, we've got two types of connectivity. On one side, there is the central FPS infrastructure, which we also call scheme. And on the other side, we've got participants, which are partner banks that are using Form3 services. When Scheme is trying to connect to us, they are initiating 7 types of connections per client, and can be multiple connections of one type per client, depending on how much traffic they have. And we need to keep track of all of them on our HAProxy boxes. So the configuration gets quite involved. We also run 2 auxiliary processes on those boxes. First is the data plane API, which we use to configure HAProxy dynamically. And the other one is KeepAliveD, which is used to do a seamless automated failovers from one data center to the other in case the primary one fails. Next on the traffic path are our Kubernetes nodes, which are listening on kube node ports, and then forward traffic to appropriate FPS gateway pod, which is running the FPS application logic for that customer. On the other side, we've got participant connectivity, and participant can connect in one of 3 different ways to Form3. First and foremost, we've got our Form3 CRUD API, which lets customers create and delete payments, send the payments, create and delete accounts, etc. 2, we've got this Web Services API, which is just a SOAP API, and IBM MQ, which is a message queue. Those 2 are legacy interfaces which help customers to migrate later on to our API. IBM MQ is a message queue that places a requirement on us that we have to keep long-running TCP connections. If they break, they cut into our SLAs, and that's bad. So that was one of the considerations that we had to take into account. And when we are communicating with participants, the communication is kinda non-symmetrical, because when participants are connecting to us, there was a requirement that they have to connect to a single IP address, because those are old protocols. So we accommodate that using floating IPs, which are implemented by KeepAliveD, which helps us do the failovers if the primary data center fails. But the other way around, participants just have to whitelist HAProxy's IPs so that we can send traffic to them from either side. So on one side, we've got active-passive scenario, and on the other one, when we are trying to communicate with them, it's an active-active one. Next, we've got security requirements, which for financially regulated businesses are really important. So first, we've got mutual TLS authentication so that we can confirm with whom we are communicating. The second point is source IP validation. Because we all are running static IP addresses, we can easily validate them on the firewall, but we also do it on HAProxy, just to be double sure. And we also, last but not least, we also do frequent maintenance infrastructure rebuilds. So we rebuild the whole infrastructure in the data centers from ground up to ensure that we are not running any malicious software. So in the end, our architecture isn't that complicated thanks to HAProxy. So on the left, we've got whomever wants to connect to Form3, and then we've got a firewall, and then we've got HAProxy boxes, and in turn, we've got our Kubernetes clusters. When we are trying to connect to the participants, we've got the custom load balancing algorithms that we want to abstract from the applications. So all of that is implemented and configured in HAProxy config. To accommodate that, we create a Kubernetes service, which then redirects traffic to the HAProxy so that it is completely transparent to the application. The application just talks to that service. And this whole setup, HAProxies and services, is configured via our custom gateway operator, which is a piece of code that talks to the data plane API and configures HAProxies. And on the other side, it also creates the services for our applications to connect to, so that all of that is transparent. And back to you, Brandon.
Thanks, Piotr. So, as some of you will be aware, it is possible to achieve API-driven configuration of HAProxy via a service known as the Data Plane API. So this service runs as a sidecar process to HAProxy and effectively translates API payloads into on-disk configuration changes. It also manages the process reloads where necessary and brings with it several benefits over directly managing the configuration line by line on disk. Firstly, it provides many abstractions. So while the Data Plane API maintains all of the HAProxy terminology that we're familiar with, i.e. front ends, back ends, servers, it also provides some very useful abstractions to ease the management burden where necessary. So one such concept, as you will see on the slide, is the site farm. So this is an abstraction which makes it easy to create a simple site, which is a front end with one or more back end servers. Depending on your use case, this kind of abstraction will either help or hinder. Of course, when you sacrifice configurability, things become easier to configure, but there is less control over that configuration. In addition to this, the Data Plane API is transactional. This means the user can build multiple changes into a single transaction. So, for example, if you wanted to delete one backend server, add another backend server to replace it. If you were doing this in a non-transactional manner, you run the risk of one of these changes being successful and another failing, and ending up in a situation where you either have too many or too few backend servers. With the Data Plane API, you build these all together into a single transaction and you commit it. If any step of the transaction fails, it will be rolled back and not committed. If it all succeeds, then your transaction is successful. Either way, you end up in the old known good configuration or the new desired configuration. Now, a very abrupt change of topic, but I promise it is all going to come together soon. We will now look at Kubernetes operators. So, an operator in human terms is someone who looks after a specific application or set of applications. They will have a very deep knowledge about how the application is built, deployed, configured, and what to do when something goes wrong. People who run such workloads on Kubernetes or otherwise will often want to make use of automation to minimize the amount of manual work they have to do. It is obviously much easier for software to repeat a task safely, and it's much easier to scale software than it is to scale human operators. So the Kubernetes operator pattern captures how you can write code to automate the task of a human operator beyond what Kubernetes itself provides out of the box. Kubernetes operators make use of a pattern called the control loop. In robotics and automation, a control loop is essentially a non-terminating loop which regulates the state of a system. The most familiar example for almost all of us will be a thermostat. So when you go up to your thermostat, you set the temperature. You are telling the thermostat the desired state of the room. The actual temperature of that room would be your current state, and the thermostat acts in a control loop to try and bring the current state closer to the desired state by, for example, turning on your air conditioning, turning on or off radiators, etc. So in our case, we are talking about observing the current state of HAProxy configuration. We're talking about calculating the difference between this observed state and our desired state, and updating the HAProxy configuration on disk to align these. This leaves the question of how do we know the desired state given such a complex architecture? The missing link in all of this is Kubernetes custom resource definitions. So fundamentally, a custom resource is an extension of the Kubernetes API and will provide something that's not necessarily available in a default Kubernetes installation. That is to say, it is customizing your particular Kubernetes installation. However, it is worth noting that many core Kubernetes functions are now being built using custom resources, just to ensure that Kubernetes stays as modular as possible. So on their own, custom resources let you store and retrieve structured data. When you combine a custom resource with a custom controller, these custom resources provide a true declarative API. That is, you can declare the desired state of your resource, and the controller will keep the current state in sync with your declared desired state. That is in contrast with an imperative API, where you explicitly instruct the server which steps to conduct in order to get to the desired state. So in our use case, firstly, we declare at a high level in YAML the desired state of a given organization, that being their network ingress, egress, security configuration, load balancing algorithms, etc. The operator observes that an organization resource has been created, updated, or even deleted. It will then execute its control loop to ensure that the low-level HAProxy configuration matches the high-level desired state. And finally, as we will see soon, the operator updates our organization resource with fields such as finalizers. And this will be covered in our demonstration. So, to conclude all of that, this means that any undesired change to our HAProxy configuration, be that a virtual machine rebuild, manual changes on disk, etc., will be detected and rectified by the control loop, and any changes to our organization resource will be propagated by the control loop to HAProxy. This gives us a repeatable, automated, reliable, and easily maintainable translation layer from the business logic to HAProxy configuration, which really gets the job done. I will now hand over to Piotr for a demonstration, which will tie all these concepts together in a real-world example.
Okay, let's jump right into it. On the right-hand side, we've got kind Kubernetes cluster, which is a Kubernetes cluster running locally. And we've got two pods in the default namespace. The first one is the custom gateway operator that we wrote, and the second one is the HAProxy pod. On the left-hand side, we've got our CRDs that we'll be applying in this demo, and the service that we'll describe in a moment. Let's display one of those CRDs. So as we can see from kind, it is an inbound frontend CRD with a name customers. It has its custom specification. In this case, we are configuring a backend, and we are looking for that service to forward traffic to. This is the service here. And we've got some TLS details for that connection. There is an HTTP mode, and we've got some bind details, TLS specification when participants are connecting to us, and of course, traffic type, which in this case is web services. If we go to logs on the right-hand side, logs of the operator, we can see that there is nothing there. And if we try to apply those manifests, we can see that some logs are popping up on the right. If we filter them to the relevant ones, we can see that the operator has successfully reconciled on two objects. One of them is the inbound frontend, and the other one that we didn't see is the organization one. Now, if we go to the HAProxy pod and display the configuration, there is some test configuration, generic one, and we've got our frontend configured here. This is the customer's frontend with most HTTP that we've seen, bind details here, some TLS details as well. We didn't see the organization, but it specifies the CNAME for that particular organization, which in this case is bigbank.com. We look for the path and verify the IP address of the originator, just to be double safe. If we now try to display this organization CRD in Kubernetes, we can see that in the metadata section, we've got a new field, which is finalizers. This field is a list of strings, and if it's not empty, Kubernetes only marks those objects for deletion, but it doesn't delete them from etcd unless this list is empty. So operators use it to do some finalization work when the objects are deleted. They get the event, they do their work, and then they delete themselves from this list. We can see that in action now by deleting this organization. I don't know if that will be visible on the video, but it takes a fraction of a second. It is not immediate, so that the operator can do its work in the background. And we can do the same for inbound frontend. Let's delete it. And if we go back to the HAProxy pod and display the configuration, we can see that it still has this generic test configuration, but there is no custom frontend anymore or backends for that traffic. And that's it for the demo. Thank you for your patience, and I hope to see you around.
Excellent. Brendan and Piotr really enjoyed that talk, and we have the gentleman in the virtual flesh here today. So, gentlemen, thank you so much for joining us.
Yeah, no worries.
Thank you for having us.
It's been a pleasure.
Great. So we've had some questions come in. As a reminder to the audience, you can submit questions in the stream Q&A as well as in the HAProxy community Slack channel. And you can also use on social media, on Twitter, you can use hashtag HAProxyConf, and our team will be picking up questions there as well. So let's get into a few of the questions for the audience. Feel free, either of you can answer or you can both chime in. So the first one I have is, you use the HAProxy data plane API in what you call API-driven configuration of the load balancer. When should people consider using an API to configure their load balancer versus editing the configuration file directly?
Yeah, so I can take this one. I guess it depends on a few things. So it depends on sort of where you are in your career, I guess. Like if you're a student or you're just learning HAProxy, you probably want to use the files on disk because you get to learn how it really works at the core, right? If your configuration is static, as in you're going to write it today, it's not going to change for 3 years, 4 years more, then by all means bake your config onto a VM or into an image. But if it's in any way dynamic, you want to be able to change it quickly, you want to be able to change it safely, then I would always suggest the data plane API. And we have rubbed up against some issues where the data plane API maybe doesn't have support for a certain thing, but it's open source, right? You can go add it. It's a fairly quick turnaround. So I would always recommend the API unless you want to learn, to be honest.
Yeah, and I really like the first part of your answer. You, especially for people early on in their careers, they shouldn't shy away from learning how the sausage is made because that can be a good learning
100%. Otherwise, the abstraction
Great.
is just confusing, right?
Sure. Okay, so the next question we have is, okay, this is about custom resource definition. Okay, so you described a custom resource definition in Kubernetes. In your opinion, is this the future for Kubernetes as you see it? And can you also try to help viewers understand the reasons you decided to create a CRD in the first place?
Okay, I can take this one. It's a really interesting question because it all seems that there is a lot of software created based on CRDs, like Prometheus operators, for example, and other. There is a lot of it in the CNCF landscape, basically. But and I've listened to an interesting topic on last KubeCon, and the guy was talking about a general purpose control plane for Kubernetes. This is basically Kubernetes, but you eliminate all the stuff like node workers, all the scheduler. You only leave Kubernetes API server, etcd, and controller manager with several controllers in there, and you use it as a general purpose control plane. So you can add CRDs there in the usual way with the CRD definitions, or you can even create your own API for handling CRDs. And you add your controllers there so that they can handle infrastructure outside of Kubernetes, like provisioning, load balancers, etc.
Excellent. Thank you so much for that detail. So we're just about out of time. I guess what I'd love to leave with is, are there any parting thoughts that either of you have that you'd like to leave with the audience?
So I guess from my perspective, it's very much that the HAProxy ecosystem is way more complex than I ever thought it was. A year ago, it was kind of just a load balancer to me. And you had one config file and it just ran, right? You would install it on a server in a cupboard somewhere. But it is way more complex and way more mature. And also way more progressive at the same time. Than I knew or believed. So yeah, if you think you can't do something with it, go have a look. You probably can.
Excellent.
Yeah, I can double that.
Excellent. Well, great parting words. Thank you so much for that. And Brendan and Piotr, thank you so much for joining, for putting together the presentation. I thought that was really enjoyable, and for joining us in the live Q&A. So really appreciate it. And now you get to relax and enjoy the next 2 days of the conference. So thank you so much both for joining.
Yeah, thank you very much.
Thanks a lot.
Have a good conference.